We now come to the last session on this day. We have two excellent speakers here in the front rows. The first one I introduce Mr. Zhao. He comes from the Free University of Berlin and has a topic you see, rule-agent-oriented scientific workflow execution. I'm very proud to see you in Deggendorf. Mr. Zhao, please, your entry.
Thanks, and good afternoon. Okay, my topic is rule agent-oriented scientific workflow execution, and first I will give a brief introduction about scientific workflows, and then I will introduce major challenges in the scientific workflow domain, and then I will propose our rule agent approach, and last I will present our prototype system. So what are the scientific workflows, and why scientific workflows are very important for scientific research? And we know that currently there are many complex steps in the scientific processes, and with the rapid development of information technology, there are a great number of resources available on the internet, and scientists are increasingly prefer to use these resources to perform their experiments. So as a main programming approach to develop scientific applications on the distributed environments, scientific workflows enable scientists to streamline a group of small tasks into more sophisticated ones and liberate scientists from some time-consuming activities or troublesome activities. And in our work, we classify scientific workflows into two types according to the process repetition. And they are production workflows and weakly structured workflows. And the production workflows have a higher repetition rate. And the goal of production workflows are used to improve the efficiency of workflow processes. And they have the routine processes and static data dependencies, and they are also usually predefined in advance in build time, and they don't need to modify their logic at the runtime. But compared to the production workflows and weakly structured workflows, have lower repetition rate, and they don't have static logic, and their logic often changes. So, for example, if they in order to get a useful result from scientific workflow, and scientists may change their logic several times to see which instance can generate the useful result. And moreover, at the heart of these processes are few activities. They are often done with uncertainty. And we further classify weakly structured scientific workflows into knowledge-intensive workflows and exploratory workflows and loosely structured workflows. And knowledge-intensive workflows, and there are usually some knowledge-intensive tasks in the workflows. They are usually decision-centric or goal-oriented, and these tasks are usually performed by the domain experts based on their experiences or their comprehensive knowledge. And the exploratory tasks are usually involve some exploration of variants or configurations, and scientists usually, for example, they may modify the parameter values and to see which one could generate the useful result. So exploratory tasks, they are one-of-a-kind tasks. And the third type is loosely structured scientific workflows. And there are some scientific workflows sometimes have some special requirements. And for example, currently there are many scientific research projects need the collaboration between different research groups. So it is necessary to build some collaborative scientific workflows to facilitate the collaboration between these research groups. And we identified three major challenges in the scientific workflow domain. And we know that the scientific workflows are usually executed in the distributed environments. And although the distributed environments provide a great number of resources available on the internet, and these resources are usually heterogeneous in nature, which means they are represented in different forms. They may be web services or Java classes, or they may executables or scripts. And moreover, they are also dynamic in nature, which means they may join or leave the environments at any time. And the second challenge is that although weakly structured activities have a lower repetition rate, but these weakly structured workflows are very common in the scientific research, and they have knowledge-intensive tasks and exploratory tasks and all those structured structures. So, for the traditional program languages, these weakly structured activities cannot be easily described by these traditional program approaches. And the third challenge is that currently many scientific workflow management systems only support the centralized workflow execution, and they cannot support some decision-centric or problem-oriented or decentralized and collaborative scientific workflow models. Before we go to our rural agent approach, first I would like to introduce a use case from the European Distributed Institute of Taxonomy used to identify newly discovered specimens. And we can see there are three actors in the progress. And the first actor is a fieldwork participant. And the fieldwork participant first discovers a specimen and discovers its features, and then sent it to a taxonomist to identify. The taxonomist, the second actor, and receives the specimen description and identify it based on his experience or knowledge, and send the result to the curator for management and to the fieldwork participant respectively. And we can see some common features in this progress. Firstly, and there are each actor has its internal behavior, and they also need to interact with other actors to complete the specimen identification. And the second, we can see the most important step is the second step, and here the taxonomist need to have and he should be experienced and have the knowledge to identify the newly discovered specimens. However, but the specimen identification here means the logic of specimen identification are usually decision-centric because it may involve many various types of specimens, and this logic may also be changed. For example, if some specimen extinct or a new specimen discovered, and the logic of the specimen identification must be modified. But for some traditional program languages, and the logic are usually buried in the workflow, the languages, and they cannot be easily modified. So we propose our rural agent approach. To be precisely, we propose a rule-based scientific workflow specification and combines reaction rules and derivation rules. And reaction rules are used to describe the task dependencies and data dependencies. And the derivation rules here used to describe the complex scientific logic, especially for the logic of knowledge-intensive tasks or exploratory tasks. And the execution environments of scientific workflow execution consists of the distributed inference reagents, and the interaction between these reagents are implemented where the asynchronous sending and receiving event messages. And we also support a simple human interaction-based exception handling at runtime if some knowledge-intensive tasks cannot be performed by the human raw agents. In these cases, domain experts or human may be involved to make decisions at runtime. This is the architecture of our raw-based scientific workflow approach. And we can see these are raw agents, and for each raw agent, it has internal behavior, and they are described by the derivation rules, and the interaction between these raw agents are described by the reaction rules, which means a raw agent is waiting for the external events from the other raw agents to start. And here, these raw agents are connected by an enterprise service bus. And here, this is the human agent. So if there are some exception arise in the at runtime, so the human agent will be used to make decision at runtime. To implement our protest system, we employ PROA, which is an open source language for reactive agents and event processing. And PROA stands for the logical programming language Prolog and object-oriented language Java. And so it combines the benefits of declarative, imperative, and functional programming styles. And it also supports the loosely and decoupled interaction between the raw agents. And moreover, it can be easily translated to the interchange stance reaction raw ML. To support the interactions between these distributed raw agents, and PROA provides three message constructs to send and receive messages, and they are send message and receive multi-message. And the difference between receive message and receive multi-message is that receive message construct works only once, and receive multi-message works indefinitely, and it can receive any number of messages. So it is very useful for the server side. And the messages in this construct are described by the position-based arguments. And we can see they have the conversation ID and message protocol, and the sender agent and the receiver agent, and the argument performative here denotes the pragmatic context, and the last argument is the content of the message. And we know there are many workflow patterns. So since our workflows are event-driven, so we need to process a complex event at runtime. The PROA supports the complex event processing based on collective reactions, and currently support two logical reaction groups, and 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 OR. And AND requires all event messages to be successfully received. And if any event message isn't successfully received, and the whole progress fails, and the OR requires any event message, any required event message to be successfully received, and if any required event message received, and the other event messages are ignored. And PROA also supports other group annotations to describe the complex workflow patterns. But here I don't want to go to details. And so if you are interested in them, I will show you after my presentation. This is an PROA example used to detect some suspicious login, and we can see on the server side, and the receive multi construct is used to receive any number of login event, and after it received a login event, and the predicate server underline 1 predicate is used to detect the further events. We can see this receive message construct. It is used to detect a logout event from the user. And this receive construct is used to detect the login event of the user from a different IP in 1 second. So, and we can see this receive message construct and this one, they belong to a same reaction group G1, and G1 is a AND reaction group, which means if a logout event followed by a login event from different IP in 1 second, we can conclude this is a suspicious login. And this is all parallel pattern, workflow pattern implemented by our agent-based approach. We can see there are 2 tasks in this progress, and task 1 and task 2, they are executed in parallel, and task 1 executes after it receives an event B, and send an event D after it finishes, and task 2 execute after it receives an event C, and send an event E after it receives. It finishes. So we can see the receiving of event D and E, they belong to same reaction group P2, and P2 is an all reaction group, and so which means either arrival of event D or E triggers the rest of the process begins. As I mentioned before, we connect distributed ROR agents with the enterprise service bus, and in our prototype system, we employ ROR responder as our agent communication middleware, and ROR responder is also an enterprise service bus based on Mule, and it supports the ROR-based collaboration between distributed ROR agents, and it supports each ROR agent to use their proprietary ROR languages, and the interaction between these ROR agents and they use interchange ROR language reaction ROR ML, and PROA, the ROR responder is also very highly scalable and reliable application message framework because it uses staged event-driven architecture in it. So here is a more detailed example used to identify various ants from all over the world, and we can see. Actually, this example is derived from the use case I mentioned before, and the 3 actors are here, and for each actor there is a ROR agent performs its tasks on their behalf, and besides their internal behaviors, there are many messaging activities and used to interact with each other. For example, we can see a fieldwork participant ROR agent need to send the ant description to the taxonomist ROR agent and receive the result from it. And the taxonomist ROR agent need to receive the ant description and send the result to curator for management and for fieldwork participant ROR agent respectively. And here the curator ROR agent need to receive the identification result from the taxonomist reagent. This is a Prova code snippet used to identify the various ends in derivation rules. We can see there are two parts of derivation rules, and the bottom parts are facts, and they describe the features of various ants. And we can see that, for example, Argentina ant has one node, and their color is light brown, and their thorax is uneven. And the little black ant has two nodes. Their color is black, and their thorax is also uneven. And so these facts are very understandable by domain experts, and they can and moreover, these facts can be easily modified. For example, if some ants extinct or a new ants is discovered, scientists just need to add some new facts or remove the corresponding facts from it. And the concrete logic of ant identification is implemented by the rules. We can see the ant identification rules is used to prove the variable x is a certain ant if it meets the following features, for example, body features and next features and feeding preferences. And the concrete processes in the taxonomist reagent is implemented by the reaction rules. We can see first the taxonomist reagent receives the ant description from the fieldwork participant reagent, and the features are stored in these variables for the next and body feature and feeding here, and the variable x here is used to store the result of the identification, and this predicate identification triggers the concrete logic of identification, and it triggers the logic in derivation rules, and stores the result in variable x. So if x is successfully bounded, we can see, and then the taxonomist reagent sends the result to the fieldwork participant reagent and the curator reagent respectively. But if the identification is failed, and which means the x isn't bounded here, so the taxonomist reagent need to send the exception to the human agent, and the human agent here is also a reagent, but it's implemented as a Java servlet, and it has a user interface, and users can check domain experts can check the exceptions and make decisions at runtime, and then send the exceptions, his decisions back to this reagent, and after receive the domain experts decision here, and then send the decisions to the fieldwork participant reagent and curator reagent respectively. And we can see we use the derivation rules to describe some complex decision logic, and especially to describe some describe the logic in the knowledge-intensive activities and exploratory activities. And we also use the reaction rules to support some dynamic and agile workflow reaction patterns. And moreover, we support the asynchronous communication based on the decoupled event messaging. And compared to the S-BPM approach, we know the core elements in the S-BPM approach are the subjects, and based on the interaction of the subjects, and these subjects complete some complex goals. And our approach is an implementation of the S-BPM approach, but the core element in our approach is the rule agents, and each rule agent has the internal behavior, and they are implemented by the derivation rules, and the interaction between these rule agents are supported by the reaction rules. And here we propose a rule agent oriented architecture for scientific workflows, and combine derivation rules and reaction rules to describe the complex logic of scientific workflows, especially for weakly structured scientific workflows. And our future work, we know that provenance is also a very important part of scientific workflows. So after get a result from scientific workflow execution, scientists may be interested in which tools or softwares or data are used to generate this result, or how was the result was generated. So it is very important to record and manage the provenance data. And the second is that although we provide the rule-based workflow, scientific workflow for the formalism, but actually it's declarative, but we still need to evaluate its expressiveness and to see in how many workflow patterns it supports. And now there is a comprehensive workflow pattern list. So we plan to compare it with the workflow pattern list to see which patterns we can't describe, and which patterns we can describe. And here are some selected references. And thanks.
Thank you very much, Mr. Zhao, for this interesting business process type. Are questions here? So I come to you.
Yes, very interesting. However, the workflow you presented, so this classification, having the taxonomy, institution and the curator and the field researcher, this doesn't look very ad hoc or very. It seems to me like a standard workflow. So it's not that kind of scientific, easily to change workflow. So could you comment on this? So how would you, or can you give another example, which is a workflow which has to be adapted to special situations more frequently than the particular example you showed us?
Okay. You mean some example of weakly structured scientific workflows, or?
Yeah, the workflow you showed us is very well. You can establish this and use it for 20 years.
Yes. Mm-hmm.
So it's not. There's nothing
Mm-hmm.
or nothing ad hoc in this workflow. So it to me like it doesn't look to me like a scientific workflow. Well, it's obviously it's a scientific matter, but it's not the way scientific workflows usually are.
Yes. Okay. I'll give you an example from actually. Sometimes it in other scientific workflows, and scientists may be tries to select some valid data from collected from different from the weather. I think from the weather report, and to predict some. Actually, I have a very complex scientific, weakly structured scientific workflows, and scientists sometimes need to select, select the simple data based on the geography information, and they need to build a model to predict the weather, but but you know the models are different from the different places have different models, so it is they will have the different criteria to select the simple data. So for example, the highlight of the location is very important. So different places they will have different criteria. So the logic of a workflow may different in different places. So they need to modify their logic at different scientific workflows.
And the logic is modified by modifying the rules
Yeah.
using to control your workflows.
Yes. Actually, the modification is usually performed by the domain experts because the authors of scientific workflows are usually domain experts.
Okay, thank you. Another question? Another question for me. Is it possible to transfer your concepts to different other process types? Not scientific workflows, but other different process types?
You mean business workflow?
Yes, so I think logistics is a process type?
Actually, I focused on scientific workflows because I didn't consider other workflow types because scientific workflows actually more complex others because they are more flexible and they need to deal with exceptions at runtime. So, sorry, I didn't consider other workflow types.
Thank you very much.
Okay.
Another question from the auditorium? Then I would thank you for this special talk. Thank you very much.